Hey everyone, ever tried predicting something really complicated, like the weather or stock prices? These are chaotic time series, data that changes in ways that seem random but actually follow hidden rules. But here's the catch, real-world data is noisy. It's full of glitches, missing pieces, and unexpected surprises. That's where today's science comes in. Researchers are building smarter tools to make these predictions more reliable. Let's start with the basics. Two popular methods for forecasting chaotic systems are reservoir computing, RC, and nonlinear vector autoregression, NVAR. Think of them as fancy math tools that try to learn patterns from data. But here's the problem. They rely on fixed rules, like polynomial equations or random patterns, to handle complexity. Imagine trying to drive a car with a map that's stuck in the 1900s. It might work in perfect conditions, but when the road gets bumpy or the data gets noisy, it crashes. The researchers behind this study wanted to fix that. They developed an adaptive model that swaps those rigid rules for a neural network, a type of AI that learns on its own. Here's the cool part. Instead of using fixed math formulas, their model uses a simple neural network, called a shallow MLP, to create flexible data-driven rules. It's like giving the car a GPS that updates in real time, adjusting to traffic jams or road closures. How does it work? The model takes time-delayed inputs. Think of it as looking at a weather report not just today, but also yesterday and the day before. Then, the neural network transforms these inputs into patterns that adapt to the data's quirks. By training the network and the final prediction step together, the model avoids the messy, error-prone math of older methods. No more expensive matrix inversions or guesswork with tricky parameters. The results? In tests with chaotic systems like the famous Lorentz 63 model, which mimics weather patterns, the adaptive model outperformed traditional methods. It handled noisy data better, even when measurements were sparse. Imagine predicting ocean temperatures or climate shifts with more accuracy, something that could help us tackle real-world challenges like climate change. So why does this matter? Because real-world data isn't perfect. This approach bridges the gap between theoretical models and practical applications. It's not just about smarter math, it's about building tools that can navigate the messiness of reality. Let's break it down further. The Lorentz 63 model is a set of three equations that describe atmospheric convection. It's a classic example of a chaotic system, where tiny changes in initial conditions lead to wildly different outcomes, the butterfly effect. Predicting such systems is like trying to forecast a storm with a ruler. The math is elegant, but the real world is messy. The study compared traditional methods like NVAR, which uses fixed nonlinear functions to model dependencies, against this new adaptive approach. The key innovation. The neural network doesn't just fit data, it learns how to adjust its own rules. This is a game changer because it eliminates the need for manual parameter tuning, which is both time-consuming and error-prone. In experiments, the adaptive model showed superior resilience. When data was corrupted by noise or missing critical points, it maintained accuracy where others faltered. This could revolutionize fields like meteorology, economics, and even neuroscience, where chaotic dynamics are the norm. So what's next? Researchers are already exploring how this framework scales to higher-dimensional systems and real-time applications. The implications are huge. More reliable climate models, better financial forecasting, and deeper insights into complex biological systems. Stay tuned as we dive deeper into how this model stacks up against other techniques and what it means for the future of forecasting. Thanks for watching. Hit subscribe for more deep dives into cutting-edge science.